Okay. An announcement that you'll like, I think, to start with. Apparently when I made up the website, nobody seems to have noticed this, or if they did, they didn't tell me. I got some of the dates mixed up. It was like I truncated a week off the class. Did anybody notice that? No. Well, it's good. Actually, it's good news for you because assuming that's correct, which Ryan's going to check right now, that means that you actually are going to get a week longer to do your project because I think I had it due the week too early. Okay, so again, Ryan's checking it right now, but I think what this means is that there's an extra week, so everything's delayed by a week. You have a week longer to hand in your project.
Okay, so, sorry.
Right.
April 27th and April 29th will be the course conference instead of the 20th and 22nd. But we have the project due Monday, May 4th, so we'll just keep that version.
Okay, so I retract that. the due date was wrong, but still the course conference will be a week later though.
Yeah, and that'll be less. Then they have more time to prepare.
Right. And that means we have 2 weeks to do extra topics instead of 1 week. Okay. So only one person wrote me with suggestions. So if you don't suggest things, we'll pick them. Okay. Let's continue with concentration and measure then. The last thing we had talked about was given a class F, we have this measure of complexity, which is the Rademacher complexity, which is sort of how correlated can we make an arbitrary function F with noise. The sigmas are like noise. And we'll see in a moment why this quantity pops up in the proof, but generally we don't compute it. We bound it by the shattering number. So let me remind you what the shattering numbers are. Some of you have seen this. If you took 705, we talked about this briefly. And you should have seen it a bit in 701. I'm just going to close the door just a second. All right, I'm back. Were you worried I wasn't going to come back? Okay. So shattering numbers are easier to compute, and they put a bound on this. What's a shattering number? Let me remind you. So suppose now that the class F is a set of binary functions. That is, each F is mapping some set, let's say script Z, into 0, 1. So this is like, for example, a classifier is the canonical example. So F can only take values 0 and 1. You can also think of an F like that, though, as a set, right? If I take an F which is 0, 1, that defines a set. Namely, let's call it A, which is the set of Z's for which F of Z is 1. So I'm going to just go back and forth between talking about binary functions, which you can think of as indicator functions for sets, or just the sets themselves. They're equivalent. Every set corresponds to some binary function. Every binary function defines a set. So sometimes it's convenient to talk about class of sets. So corresponding to F here then is a class of sets. Right? Is that clear? Okay. So so I'm just to draw a picture of that. Here's a binary function, 0, 1. But you can just think of it as defining this set A. That's the indicator for A. So sometimes we'll talk about the shattering number of F or the shattering number of script A. It's equivalent. And so what's the shattering number? So first of all, let's talk about the projection of a class F. Remember, we're talking about a class of functions, so think of it as a collection of classifiers. And given some fixed finite vector, say Z1 to Zn, let's define script F Z1 to Zn. This is the projection of the class F onto the vector Z1 to Zn. Is just the set of possible vectors you get when you apply the function there. So I take a function in the class, I evaluate it at these endpoints, that gives me a vector. It's a binary vector, right? Just zeros and ones. And that's the set of all such vectors. Okay. All right. Then the shattering number is just or the growth number, as some people call it, is just how many such how many such vectors I can get. So we'll call it either Sn of f or S of Fn. Or again, if we're thinking about this as a class of sets, we'll write it as S of A. And it's just how many such vectors are there here. It's just, if I look overall, choices of z1 to zn, how big is this collection of vectors? Okay, that's called the shattering coefficient or the growth function. It's another measure of how complex this set of functions is. Let's just do a simple example just to make sure that you remember this. So let's take, we have to choose a collection of functions or sets and an n. So let's take, as our sets, let's take all sets of the form minus infinity to t, where t is on the real line. Or equivalently, all functions that are 0 and then 1. And let's take n equals to 3. So now if I pick any three numbers, let's say z1 less than z2 less than z3, let's think about the possible values I can get when I evaluate a function of this form. So I have a function like this. What are the possible bit strings I can get? Well, I could get 1, 1, 1. If I go over here, I can get 0, 1, 1. I could get 0, 0, 1. And I can get 0, 0, 0. And so that's 1, 2, 3, 4. Did I count that right? 4 of them? Yep. So that means that S3 of A is 4 in that particular example. So it's fun to do this. Take the set of all circles in the plane, all disks in the plane, and figure out if I plop down some z's and I look at the bit patterns I can get, what's the biggest I can make that? Again, I'm assuming most of you have seen that before. The important thing, of course, is that there's a maximum on this shattering coefficient. Which is, what is the biggest this can be? Vectors of length n to the n. So the interesting thing, of course, is when this is less than 2 to the n. And that's why this measures the complexity of the class, is because if it's 2 to the n, it's saying there's lots of functions in there. No matter what pattern you want, I can produce it. But if it's less than 2 to the n, that's not true. Okay. In fact, a set A is shattered precisely when you can find every possible bit pattern, or we can pick out every subset of the set. So there's some basic properties of shattering numbers that are in Theorem 15. They were actually, I think this was a homework question in 705, if I remember correctly. So you can look at those, like shattering number of A union B is the shattering number of A plus the shattering number of B, and so on. So if you haven't seen those before, look at those right there, and you can just review them. But the one we're interested in here is we're going to prove that there's a connection between the Rademacher complexity and the shattering number. And the shattering number is something we can compute, whereas the Rademacher complexity typically would be something it's not obvious how to compute. And so here's a bound that relates them, and we'll prove this now. So the Rademacher complexity, now we're talking about, though, a class of binary functions. And we're going to prove that this is less than or equal to the square root of 2 over n times the log of the shattering number. So let's compute that. So this is equal to the expected value of the soup over f. And let's call this, in the notes I just called it SF sigma. That's just the thing that's inside the Rademacher complexity. That's this thing. Okay, so this is just the definition, right? But there's two sources of randomness here. There's the Z1 to Zn, and then there's the sigmas. So the trick here is to rewrite this as a double expectation. We first condition on the z's, and just take the expectation over the Rademacher random variable. So this will be conditional on z1 to zn. So think of z1 and zn as fixed now. And then the thing is, so these are all 0 or 1. This is plus 1 or minus 1. We can now just think about how many possible values can this thing take? Well, all that matters here, when we think about this, think of this as n numbers now, right? F of z1, f of zn. Those are binary patterns, and we've already said the maximum number of those is given by the shattering number. That's the definition. In fact, you can just think of this as a vector. If we just define the vector v to be f of z1 to f of zn, I think I even wrote it this way in the notes, that this is just saying what's the expected value of the maximum over all such v's, and I'll write it like this, of S of v sigma given z1 to zn. I'm just emphasizing here that these are just binary vectors of length n. Okay. Now, if we look at these, so this is just sigma I times vi, it's just some number. But what we notice is that, so I'm calling this vi, and what we notice is that, of course, this is always true. I'm including, I should say, the 1 over n here. Right? Because these are just plus and minus 1, and these are 0, 1. So what do we know about random variables that are bounded? Well, we know that their moment generating function we had a theorem that said the moment generating function could be bounded. I'll just remind you what it is. In this case, it's no, sorry. Okay, so that's just applying the fact that we have bounded random variables, and also, well, bounded random variables, and so we know how to bound the moment generating function. Now, I reference ahead to something called Theorem 30. This is something that you actually did on a homework assignment. I think Ryan assigned this question. We also did it in 705, or at least we did some version of this, which is that anytime you have random variables with a nice exponential bound on the moment generating function, that gives you a bound on the expected value of the maximum. Okay, so this is actually, I referenced ahead here to Theorem 30. I'll just tell you what it says, which is that any time, in general, if this is true, anytime we have an exponential bound on a moment generating function, we have the very useful property that the expected value of the maximum of the xi's, in general, when you take the maximum of n things, the maximum could grow like n. But when you have this condition, it doesn't grow like n. It grows like the root of log n. Is that what you had them prove, Ryan? I can't remember. Yeah. So you proved this or something like it.
They proved it for Gaussians.
You proved it for Gaussians, but it's the same for anything with a moment generating function like this. So the proof is you have to look ahead a bit. It's only 3 lines long. It's theorem 30. Okay, but I think we did it in 705 too. But if you've forgotten, just look at it. It's a very short proof. The point here is that by conditioning on the z's, we've just got ourselves into a very simple situation now, that we're computing this sum, or this average. We have a bound on its moment generating function. And the important thing is this is the key. We started by taking a soup over a class of functions. But when you take a soup over a class of binary functions, the set of function values that it can actually take over any finite set is just a maximum over vectors. So we're precisely in this situation. We're taking really the expected value of a maximum. And what is the maximum number of vectors? It's the shattering number. That's the definition of the shattering number, right? So this is less than or equal to, just using that bound, it's actually 2 times log times the number of vectors, which is the shattering number, over n. And then we have to take an outer expectation, but there's nothing left to take. The expected value, so it's a constant now. That's all there is to it. So binary functions are easy because we don't have to worry about every possible value the function can take. We don't have to worry about, in terms of Rademacher complexity, the values the function can take at some finite set of points, which now reduces it to a bunch of vectors. And the number of such vectors is the shattering number. And then we use our bound on the maximum expected value, and we have this relation. So what does that mean? It means if I don't know how to compute this, at least I can just replace it with this, assuming, of course, I can compute the shattering number, which obviously we can, or we wouldn't be talking about it, at least in some cases. But we don't just stop there, usually. Next, we define the VC dimension. So how many of you have seen the formal definition of the VC dimension? I know more of you than that have. Come on. Oh, you just, all right. I was going to say it anyway. It's not like I won't tell you. All right, let me remind you then what the VC dimension of, and again, you can think of it as a class of binary functions, or if you prefer, a collection of sets. And the best way to think about it is from the following plot. If we ask ourselves, what is the shattering coefficient of this class of sets, or class of functions, as a function of n? We know it's bounded above by 2 to the n. That's the worst case. So if I plot the function 2 to the n, it's going to look like this. But for many classes of sets, what will happen is it will be equal to 2 to the n and then stop being equal to 2 to the n at some point. In that little example we just did, for example, we did 3 points. And we saw that the number of vectors we could construct was 5, but 2 to the 3 is 8. So that was an example where the shattering number was 5, which is less than 2 to the n. So this will often be the case. We look at the shattering number and we look at the maximum value the shattering number can take, and it will be equal to 2 to the n until you get to some n. And at that point, 2 to the n keeps growing, but the number of subsets the number of binary patterns I can construct is strictly less than 2 to the n. That first point is called the VC dimension. So let's write that down. The VC dimension is the largest n such that the shattering number is equal to 2 to the n. It's the last time these two curves are the same. And this could be infinite, but if it's finite, we call it d. So this is d right here. So if f is really complicated, if it's a super complicated class of sets or class of functions, I'll always be able to keep constructing any binary pattern no matter how big n is. That's a complicated set. That would have VC dimension n, infinity. But for a sufficiently simple class of sets or class of functions, there'll be some point when I can't do it anymore, like the very simple example I did at the beginning. And that point measures the complexity of the class in some sense. It's saying you can't construct every binary pattern after this. So that's called the VC dimension. Having finite VC dimension, I should say, is a strong property. It's true for a lot of classes we deal with, but there's going to be lots of examples where it's infinite as well. It's almost like saying it's a parametric class in some sense. This is kind of like, I like to think of it as like the degrees of freedom. And then, all right, so let's assume for the moment that we know how to compute this. This is perhaps trivial or perhaps very complicated, perhaps undoable in some cases. But let's put that aside for the moment and ask, what are we going to use this for? And now comes one of the most remarkable theorems in all this, which is Sawyer's lemma, which is all we know about the VC dimension is that at this point, it's no longer equal to 2 to the n. But maybe it's equal to 2 to the n minus 1. Right? It could be just a little bit less than 2 to the n. No, that can't happen. Once it's not equal to 2 to the n, it only grows polynomially. That's really a remarkable thing. It's a purely combinatorial fact. So Sawyer's lemma here, so we're on page 11, says basically that if we have a class with finite VC dimension d, then once n is large, the shattering coefficient is less than this. That is, basically think of that as n to the d. It can only grow polynomially in d. It's a really surprising fact, right? Up to now, it's growing exponential. This is 2 to the n. And then you hit this phase change where now it can only grow as a polynomial. It's a very surprising fact. I'm going to be selective about which things I prove. So I want to prove the main VC theorem. And to make sure I get to that, I'm not going to prove all the lemmas along the way. So this is not a proof I'll go through. It's there. It's just an inductive proof. And it's called Sawyer's lemma, but I'm pretty sure it showed up in a few different places around the same time. So I'm not sure if he's the only one who did it. But I want to make sure that the meaning of the theorem is clear if you haven't seen it before, which is, again, the number of vectors. Let's just write it out again. If I take f, if I take one of my classifiers, think of f as a classifier, and I apply it to an arbitrary finite set of points, and now I keep trying different points around and say, how many such configurations can I get? The answer is, if n is bigger than the VC dimension, the number of different configurations I can get is only n to the d, not 2 to the n, n to the d. So let's look at the problem of computing the VC dimension. Let's talk a bit about that for a moment. So if I give you a class of functions or sets and say compute the VC dimension, you really have to think about each one separately. And sometimes they're very simple, as I said, and sometimes they're actually remarkably difficult. And then there's various tricks people use. We're going to basically take these as given. So I made a little table at the top of page 12 of some common things, like the intervals a, b on the real line have VC dimension 2. Disks in R2 have VC dimension 3. What does that mean? So it means, if I take 3 points, I'm claiming that I can get any binary pattern. Or in other words, I can pick out any subset I want with a disk. I can pick out this point with a disk. I can pick out this point with a disk. I can pick out this point. But I can pick out these two. I can pick out these two. I can pick out these two. And I can pick out all 3. Right? But 3 is the largest for which that's true. If I go to any 4 points, here's a good exercise. Convince yourself you'll never get every possible subset of those 4 points with disks. No matter how you try to put the 4 points, you always find, oh, maybe, if I try to capture these two, I end up getting this one. Or maybe if I try to capture these two and think, okay, try rearranging the points, you'll never do it. That's why we know the VC dimension is 3. Okay, all you have to do is find one configuration for which that's true to make the VC dimension go up by 1. And so a lot of these things, you can draw pictures and convince yourself it's true, but try writing down the proof. It can often be a little bit tricky. So that's why proving the VC dimension, is sometimes very simple, and sometimes you have to write a whole paper on it. It's so complicated. Okay, so and there's certain, I think to this day, there's certain neural nets, for example, where there are upper and lower bounds on the VC dimension, but they're not known precisely. So there's some that are still unsolved, and there are standard ones where it's known. So I listed the common ones here. Closed balls and r to the d. I said less than or equal to d plus 2. I couldn't remember if it was equal or less than or equal to. Rectangles and r to the d have VC dimension 2d. Convex polygons have infinite VC dimension. That's a good homework exercise. Prove that convex polygons have infinite VC dimension. That's a good example of a class of sets that's not too big, actually, in some sense. We can say a lot of things probabilistically about convex polygons, but you can't use VC theory because the VC dimension is infinite. But for our purposes, the important thing is for most of the classes we're going to deal with is when we use classifiers and so on, or even when we do clustering and so on, you can think of it as somebody's worked out the VC dimension for us. Okay? I want to deal with what do we do with the VC dimension, not so much how do we compute the VC dimension. By the way, I should also tell you, so what we now have, let's just back up actually. So what we have is that the Rademacher complexity, which we're going to need in the VC proof, we don't know how to compute it, but it's less than or equal to, we saw 2 times the shattering number over n. But now what do we know about the shattering number? If we have finite VC dimension, that's less than or equal to something like of order, there's a log there. The shattering number was something we see of order n to the d. So when I take the log, that's of order d over n log n. So the practical import of all this is if you're using a class with finite VC dimension d, then the Rademacher complexity can be bounded by something like d over n log n. In fact, this isn't tight. There are proofs that get rid of the log n, but they're much more long, intricate proofs. I just wanted to do the simpler proof. But actually, you can get rid of the log. That's not the tightest possible result that we proved. Okay. Any questions? Is everybody with me? Because we're going to do, finally, the Vapnik-Chervonenkis theorem. This is what we've been working up to. We're now going to use all this stuff to prove this very famous result. So we're page 13, theorem 20. I have a collection, script f, which either sets or binary functions, or if you prefer, think of them as classifiers. Here's the claim, that for t big enough, the following is true. This is what we set out to do at the beginning. We wanted to say that the probability that the soup over this class, and we're comparing, let me write it this way that it's in the notes, and then I'll remind you what this means. Let me remind you what this means. That's Pn of f minus P of f. Remember, that was just notation. This is just the empirical average. This is just 1 over n times f of zi. And P of f was just the mean, the population mean. Okay, so this is just how far is the sample mean minus the empirical mean, but the soup over the whole class. And here we go. The VC theorem says this is less than or equal to 4 times the shattering number 2n So let's spend a minute staring at this before we prove it. So if we only had one binary function, we would just use Hooftings inequality, and we would be getting something like this. It's a little bit different, right? Hooftings inequality had a 2 here. There's a slightly different constant, but that's not anything of great importance. The bigger deal is that we now have this term which involves the complexity of the class. You might notice that it says 2n instead of n. And that might seem weird, but that's because of the key trick in the Vapin-Dick-Chervonenkis theorem, which is what's called using a ghost sample, which I'll explain in a minute. If you haven't seen that before, it's a good trick to know. The ghost sample is an imaginary sample, as the name suggests, also of size n. So we're going to end up with a sample of size 2n. That's why we have a 2n there. And when the VC dimension is finite, when the VC dimension is, say, d, then this is up to constants. What we saw is that this is sort of like n to the d times. I use this symbol less than or equal to squiggly, meaning I'm throwing away constants. And this is was one of the biggest breakthroughs in learning theory, which is that the complexity of the class is such that the number of configurations you can get from your classifier, that's really what this is only growing polynomially, but the probability of error is going down exponentially. So the exponential wins. So this is really a key result. Okay? So the meaning of the theorem is good. Any questions? So let's prove this. There's 2 steps to the proof. I'm wondering whether I should prove both or just the main part. Probably just the main part. I don't want to inundate you with proofs. So the first part of the proof is to use a trick called symmetrization, which is where the ghost sample comes from. So let me first explain the idea intuitively, which is suppose I just had I wanted to know how far x bar from mu could be. I want to put some sort of bound on an average x bar from mu. So we know how to do that, but one of the complications is that mu is a real number. This could take on many different possible values. And if we're trying to do something very combinatorial, which is the basis of the VC theorem, real numbers are kind of a problem. So what you might think of as doing is the following. Create a second sample. So we have our first sample, x1 to xn. Now we create a second ghost sample. So what's a ghost sample? We just imagine, for the purposes of the proof, a second sample, x1 prime to xn prime, drawn from the same distribution and independent of the other ones. And now we construct that average. So now what we do is we look at x bar minus x bar prime, let's call it. Okay? And why do we want to do that? Well, first, let me try to convince you that these are sort of going to be similar. I think that should be intuitively reasonable, right? If I have a true mean and I draw some data and get an x bar, and if somebody else went out and got a sample and got a different x bar, let's say x bar prime, you can see that the distance between these is going to be sort of like the distance between any one of them and mu. They should be about the same order, right? If 2 of you have 2 samples and get 2 different x bars, they're both going to be off from mu. So the distance between x bar 1 and x bar 2, if you just think of using, and that's how we're going to prove it, is basically the triangle inequality, and with a few other twists, that this distance is roughly going to be of the order of this distance. Does that seem plausible? We'll prove it if we need to, but
But this is a non-asymptotic statement, right?
yeah, this is going to be a finite sample statement. Yeah, so that's the clever thing about this. What I'm going to do is state this ghost proof theorem, then prove the main theorem, and then if we have time, I'm going to come back and prove this, what's called the symmetrization lemma. Okay. I just want to first of all get the intuition here that that the size of this and the size of this should be sort of comparable. Why do we care about that? because in the VC theorem, we're dealing with 0, 1 things. So this can only take on finitely many values. This can only take on finitely many values. The difference can only take finitely many values. So now bounding this is bounding a maximum over a finite set. And that's where the Rademacher complexity is going to come in. So it's going to reduce something real valued to something that's discrete. So let me state the theorem formally. This is called the symmetrization lemma. And yes, Kevin's absolutely right. This is a purely finite sample result. And here's what it is, okay? So remember, we have our z1 to zn from P. But again, we're going to imagine this ghost sample, as it's called, also from P and completely independent. And everything that's computed from this sample, I'll put a prime on it. And here's what's called, this is the bottom of page 13, this is the symmetrization lemma, which is the probability that the supremum over all functions of that difference that we're interested in, so remember this is Pn of f minus P of f, this is the thing we're trying to bound. Okay. The first key thing is the symmetrization, which says that's less than or equal to 2 times the probability of the sup between Pn of f and Pn prime of f. So this is like the 2 x bars that I talked about. And there's just some constants that are different. So what's happened is to get it to be a finite sample inequality, we ended up with a 2 here and a t over 2 here. But those are small differences. But this is reducing something which can take real values into something now, again, when these are binary valued, there's only finitely many possible values here. Everyone with me? So, any questions about the symmetrization lemma? This is called the symmetrization lemma. Okay, so I think the order should be, it's 208. I'm going to, this might seem a little bit out of order, but I think this is a good way to do it. Let me just make sure it's not going to screw up somehow. Yeah, I think this will work. What I'm going to do is I'm now going to use this fact to prove the VC theorem. Then we'll come back and prove this theorem. Okay? So let's just take this as given. So now let's finally go to the big theorem. So we're proving again, remember what the original theorem said, is that we had a bound. This was bounded by something involving the shattering number and an exponential term. So we're going to bound this. We're going to introduce this ghost sample. And remember we have this notion of these possible vectors, which now we have to include the ghost sample. So there's f, z1 to zn. Those are all the possible values the function could take on a finite set. But we also have to expand it to include z1 prime to zn prime. We know that the number of possible vectors in this set is governed by the shattering number. But the shattering number based on 2n, not n. In fact, so we're going to use this. What we're going to actually do is, because of this, we only need to bound this quantity. But let's look at this thing. It's pretty clear that the set of vectors in here, that's what these things are. This is just the average of these f's. The average of these f's. I can write that as, so I'm computing, let's just actually keep going here. So this is, I'm going to rewrite this as I did in the notes. I can just reduce this to vectors v, the maximum over all the possible vectors now that I can get v in here of less than t over, bigger than t over 2. What I mean by this is just that, you know, this sum, let's write out what it is. But again, that's just this vector. Let's call it v. So I can just think of this as sum v1, v2, vn. So I'm just writing it as a vector, just to emphasize the fact that we're talking about finite vectors. Everybody with me? I want to try to make this as simple as possible. The important thing is that this was an infinite supremum. This class of functions has infinite cardinality. But now, thanks to the symmetrization lemma, I'm talking about finite numbers of vectors. So the probability of a max, I can do the union bound, right? The probability of max is less than or equal to the sum of the probabilities. Okay, so that's less than or equal to 2 times the sum over all the vectors in that class of the probability that v is bigger than t over 2. Okay? I couldn't have done this if I hadn't done the symmetrization. The symmetrization reduced this infinite thing to just a finite set of vectors. The probability that the maximum over a finite set is less than or equal to the sum of the probabilities, the union bound. And these are just sums of vectors where these are taking values 0 and 1. So any one of these things, this is just a Hoofting thing. These are bounded. So all I'm doing is, all I have to do is apply Hoofting's inequality in here. This is just a standard Hoofting inequality. So I get 2. And because of the 2 here, that's where the 8 comes from. Instead of t, I have, remember in Hoofting there's a t squared, but that's t squared over 4 and so on. So that's why there's an 8 there. And finally, how many things are in the sum? Well, by definition, it's bounded by the shattering. That's the shattering number, right? So this is equal to 2 times 2, which is 4, times the shattering number. But it's based on 2n. And that's the theorem. Yeah.
So when we are going from the sup to the max, is that set compact so that we can even go to the max there?
If it's more than compact, it's finite, because the
For the sup part.
this set isn't necessarily compact. But the point is that the possible values that this can take is finite. So if we just think of them as vectors, it is a max. But no, the original class script f might not be a compact set. Okay, so the clever thinking in this was like kind of trying to convert this into everything, making everything discrete and just counting.
So at a high level, you said that this was a really important result, but what you're bounding here is the difference between the empirical mean and the mean of f. Can you tell me why that's such a...
Yeah, let me remind you of the bigger picture here. That's a good question. We're going to use, what are we going to use this for? Later on, we're going to use it for, this is going to tell us that if I look at the risk over a set of classifiers, like all linear classifiers, I don't know that risk function, but I can estimate it by the empirical risk. This theorem is going to tell us if the set of classifiers has finite VC dimension, then with high probability, these two curves are close everywhere. And from that fact, we will prove, and it's really just a one-line proof after that, that if I minimize this function and find the true risk of that function, that's going to be close to the minimum of this. So this is going to justify what's called empirical risk minimization, that minimizing the empirical risk with high probability does almost as good a job as minimizing the true risk. That's why we care about this. But also we'll also see this, we can use it to prove bounds for density estimation. It's also what gives us the k-means theorem, that the fact that doing k-means on the data gives you almost the same answer as what you'd get from an infinite sample from the population. So yeah, it might seem a few steps away at this point as a fairly abstract theorem, but that's where we're headed. Okay, so now let's just keep an eye on the time, because I still haven't made the direct connection to Rademacher complexity, and I haven't proved the symmetrization lemma. Maybe we should. I'm just trying to think what's the best thing to prove. I have to be a bit selective about what to prove, just because we could go on and on and on for 5 lectures. We don't want to do that. Here's the options. I could prove the symmetrization lemma, or I could show you the theorem that links all this to Rademacher complexity. Is anybody dying to see the proof of the symmetrization lemma? Yes. Okay, let's do the symmetrization lemma. I'll take that as an enthusiastic yes. It's really just, all it is the triangle inequality together with Markov's inequality. But let's write it down. It is actually a good thing to know. And for those of you who ever go on to, some of you may come into contact with something called empirical process theory, which is something that's used a lot in statistics. And this symmetrization lemma comes up all the time there too. So this is actually a good thing to know. All right. Here we go. So we're trying to prove that thing. First of all, let's find a function, fn in f, which maximizes the difference. So we have this class of f. We're taking the soup. Let's say the soup is attained at some function fn. If it's not actually attained, we can always choose something arbitrarily close. So let's just say it's attained at fn. That won't change anything. But notice, I want to point something out. Pn involves the data, z1 to zn. So this is a random variable. So the fn at which this maximum occurs is a random function. So that's important to keep in mind, otherwise the proof would be a lot easier. All right. Now I claim the following is true. Suppose I told you that Pn minus P Fn is bigger than T. So suppose I told you that, this is like saying x bar minus mu is bigger than T. And suppose I also told you that P minus Pn prime is less than T over 2. I claim these two facts imply that Pn prime and Pn are far away. And this is from the triangle inequality. Let me just draw a picture of it. Here's the true mean, P of Fn. And I'm saying suppose that this x bar prime guy is close. I put the prime in the wrong spot. sorry, I tell you that Pn, yeah, the x bar minus p is far away. But this one is close, then that must mean these are at least t over 2 away. This is just the triangle inequality. So the proof is actually right there. I'm not going to rewrite it. I want to convince you by a picture. If one of them is close, one of them is far away, then they must be far away from each other, right? Okay. Right. Ryan's close to him. I'm far from him. Therefore, I'm far from Ryan. Okay. So anyway, if you want to see the steps, it's just right there, but you just see it's just the triangle inequality. So now let's just compute the following expectation. First of all, let's write the functions down, and then we'll just compute the expectation. What we have is that the indicator function for this event, so what I'm going to do is take the indicator function for this event and the indicator function for this event, and saying that the indicator function of this times the indicator function for this, or in other words, the joint indicator, is less than or equal to the indicator function for that event. I'm just going to express it now in terms of indicator functions. So the indicator function for this being true and this is therefore, since it implies it, it's less than or equal to. Same statement, just expressed in terms of indicators. I'm just worried that I'm forgetting absolute values, but keep an eye out for those. Okay, fine. Now keep in mind that in this thing, there's two sets of random variables. There's the z1 to zn and the z1 prime to zn prime. And they're independent of each other. So what I can do is take expected values separately over each one. So I'm going to take an expected value now over the ghost sample. Okay? So with respect to the ghost sample, this thing is constant. So I get that's left alone. But this one now becomes the expected value of that. Well, that's a probability. Let's call it the probability prime, because I mean just over the ghost sample. So just treating the ghost stuff as random. This is p minus pn prime. I knew I was going to do that. Okay. Fn less than or equal to t over 2. Is less than or equal to, and again, this is all with the expected value is just a probability now. Treating just the prime stuff as random. Notice that this Fn, it's random, but it doesn't depend on the ghost sample. Okay, so this is just same statement, expected value over the ghost sample. Finally, we're almost done. I'm going to convince you that this term here is I'm going to bound that. That's going to be bigger than a half. I claim this is bigger than a half by Markov's inequality. So let me convince you of that. So I'm going to just replace this with a half. That's where the 2 is going to come from in the theorem. And then we're almost done. Once this, I put a half in here, bring the 2 up here, and take a second expectation over the whole sample, and we're going to get the result. Why is this? But let me convince you that that's bigger than a half. Well, I'm actually going to compute the probability of the opposite. I'm going to compute the probability that that's bigger than t over 2 and say that's less than a half. So by Chebyshev's inequality, if I look at p prime of, I know this is a little bit tedious, but hang in there. This is bigger than t over 2. Let's just do plain old Chebyshev's inequality. That's less than or equal to, there's a, I'm losing my spot here. Okay, there should be, yes, t squared. Good, there we are. So, this is like the probability of an x bar being bigger than something, right? It's 1 over that squared, so it's 1 over t squared. It's an average, actually, so it's n squared. There's a 2 squared on top, so there should be a 4. You have 4 times the variance of this Fn. Right? This is just probably x bar is bigger than something, is the variance of x bar times 1 over that something squared. Chebyshev's inequality. The one complication is this is a random function. However, it's binary. It never takes, its values are always between 0 and 1, and the variance of any function between 0 and 1, doesn't matter what the function is, no matter how complicated it is, the variance can never be more than a quarter. You can check that. Take any function on 0, 1, the biggest variance you can get by moving the mass at 0 and 1. So the variance is always bounded by a quarter. So this is less than or equal to a quarter, so that's actually 1 over nt squared. And where do I get the half from? I didn't tell you this at the beginning, but I said that the theorem is true for t sufficiently large. So for t large enough, this is less than a half. Okay? So I'm just going to replace this with half now. I'm going to say this whole thing is, this is less than this. This is bigger than a half. Okay, so I can put that in there and bring it to the other side. Let's make sure it agrees with my notes. Yeah, the indicated function for the soup, which is the thing we want, is less than or equal to 2 times this thing. Now, take the expected value over the remaining randomness, which is with respect to z1 to zn. That gives us the probability that we're originally interested in. Oh, sorry, one more step. Let's remember what Fn was. It was the guy that made this equal to its soup. So this is the indicator function of the soup over f. And similarly here. And now take the expected value over z1 to zn, and we get the probability that the soup over f and f of f bigger than t. When I take the expected value over p, I can just think of that now as I'm expecting value over pn prime over p prime and p. That's just the same as taking the overall expected value. That's just the overall expected value. So it's the probability of the soup, which is precisely what we claimed in the theorem. It looks longer and messier than it really is. If you think about what I did, I know it was a little bit tedious, but I really just applied the triangle inequality and then bounded something with Markov's inequality by half and then rearranged things. That's really all it is. So I hope I didn't make it seem more complicated than it actually is. But it's a very clever trick, and as I said, it comes up quite a bit. Is that in many cases, this thing just might be easier to bound. There's no unknown mean sitting in there. Okay. We got time for more fun, so let's keep going. If this is the first time you've seen the proof of the VC theorem, by the way, I suggest go over this again, right? Just look through the proof again. It's all there in the notes. There's nothing really complicated. There's just a lot of steps to it and so on. Okay, but it's worth looking at it again. All right. So now I want to prove a related theorem, which is a kind of a different way of proving this stuff involving Rademacher complexity. So you can see how Rademacher complexity comes into this. It's going to amount to the same thing. So you can think of this as a different approach. We're going to do a Rademacher style proof, but then in the end, the Rademacher complexity gets bounded by the shattering number, so you end up with a similar result in the end. Okay, so I'm looking at theorem 22, and which says the following thing. This one I expressed in terms of a high probability statement. With probability at least 1 minus delta, the sup over f of this difference that we're interested in is less than or equal to the following quantity. 2 times the Rademacher complexity Okay. So this is a slightly different looking bound. It's the same quantity we're interested in, and you can see there's two terms again. This is the kind of thing you get from Hooftings inequality again, and this is something involving the complexity of the class. So the proof has two steps. We're going to first of all show that the quantity, this is some sort of, let's look at this quantity. This is random, right? This part's random, so the whole thing's random. As complicated as this looks like a complicated guy. It has a mean. So there are two steps. We're going to show this is close to its mean with high probability. Then we're going to bound the mean. Okay, so the strategy is a little bit different. So let's call this something. Let's call it g of z1 to zn is this thing. Okay. So first of all, it is some sort of complicated quantity, right? But it is random. It's easy to check because we're still dealing with binary functions here, that if I wiggle any zi, everything only changes in these averages by 1 over n. So this complicated function has that property we talked about when I talked about McDermott's inequality. Namely, that if I take g of z1 to zn minus g of z1, and say I take the ith one and arbitrarily change it, despite how complex this is, it's easy to see everything changes at most by 1 over n. So this is less than or equal to 1 over n. This is a perfect example of how McDermott's inequality is useful, because despite how ugly this looks, this property already gives us a Hooftings style bound. It makes part of the proof easy, which is namely getting that's going to tell us this is close to its expected value. The hard part is figuring out the expected value. But we immediately have, therefore, from McDermott's inequality, I'll remind you what that says, that the probability that g of z1 to zn minus its mean, and the mean of all that, is bigger than epsilon. It's just like Hooftings inequality. So this is actually a good thing to know about, is when you do these when you have a complicated thing like that and you do the McDermott style proof, typically you do the probability bound first. You show it's close to its mean, which is the easy part. But now you need to know something about what this is in order to proceed. So this is kind of a common strategy. So this says this is close to this with high probability. That is with probability, we'll write this as with probability at least 1 minus delta. I'm going to solve for delta. Set this equal to delta and solve for epsilon. We now have that supremum, that G, is less than or equal to its mean plus this. So we've done half the proof. This looks just like the proof that I stated, except I need to bound this. So now comes the cool part. How do we bound the expected value of this horrendous thing? We use symmetrization. We introduce another ghost sample. Okay, so we introduce, let's introduce a ghost sample again. And let's now introduce, in addition, Rademacher random variables. So this is showing you where the Rademacher complexity is coming into things. Okay, so sigma 1 to sigma n, what are they? They're random variables that are equal to +1 or -1 with equal probability. So the first thing to notice is that this has the same mean, obviously, right? The ghost sample and the original sample have the same mean. That is, if I take the expected value over the ghost sample of this, you know, everything's IID here. Everything's from the same distribution, so that is the same mean. But now comes a really interesting observation. Let's look at 1 over n times f evaluated What I'm doing here is looking at the empirical sum over the ghost sample and the original sample. This is equal in distribution, I claim, to this. If I throw in sigmas, I'm claiming that if I throw in the Rademacher random variables, I'm not claiming these two numbers are the same. I'm claiming they have the same distribution, right? Is that clear? Because if I just, all I'm saying here is if I take two random draws from some distribution, and if I now multiply this randomly by +1 or -1, it doesn't change the distribution, right? Because everything's IID. x1 minus x2 has the same distribution as x2 minus x1 if they're drawn IID from the same distribution. The number won't be the same, but they have the same distribution. So I can put this in and say this has the same distribution as this quantity. Okay. Why do I care about that? Because now I'm going to do the bound. So at the top of page 16, I think we have just enough time to do this, that the expected value G1 expected value of that soup P n of f but look at this. I can change P of f. This is just saying that mu is equal to the expected value of x bar, right? The population mean is the expected value of the sample mean. So I'm going to put that in. I'm going to go a bit fast here, so make sure we get through this. So I'm just saying that this is equal to, I'm replacing this with its expected value of the sample version. That's like saying expected value of x bar is mu. But then I'm going to take the expected value on the outside. I'm losing my brackets here. That's less than or equal to, if I bring the soup on the inside, it can only make it bigger. So it's the expected value prime of the soup which is precisely this thing we were talking about. Pn of f and Pn of f prime are just these sums, but they're equal in distribution to this. Okay, so that's equal to the expected value of the sup times 1 over n times, we're almost done. I know everybody's getting antsy. So yeah, put the ghost variables in. Then I can throw the Rademacher variables in, symmetry. But take the triangle inequality. This is less than or equal to one of them plus the other one. They have the same distribution. It's the same term twice. And what is that term? What is the, if I just had one of these, if I just had this part, what's the expected value of the sup of this? That's the definition of the Rademacher complexity. So if I do the triangle inequality, this minus this is less than this plus this. This is just 2 times the Rademacher complexity. Okay, I know I whipped through a lot of that really fast. And I didn't get to show you how to use this yet, so probably we'll use it. So here's the plan, because we're starting to run out of time. But let me just back up and say, we've seen if I want to get bounds on the probability of a supremum, now we have 2 different methods. One is directly to do it with the VC approach, which does it in terms of shattering numbers. And that uses that symmetrization trick. The second one is to use this Rademacher approach, which is to look at this supremum that we're interested in, this G, use McDermott's inequality to bound it from its mean. That's trivial. But now the hard work is trying to bound the mean. But we can do that by, again, introducing a ghost sample plus Rademacher variables. And instead what we get is, instead of shattering numbers, we get a bound in terms of Rademacher complexity. However, we know this is also bounded by the square root of the shattering number. So it gets us back essentially to the same place. It's 2 different ways of doing the same thing. And you can see why the Rademacher complexity kind of sneaks into things. It just gives us something that we can control. What I want to talk about, so maybe I know it's a lot to take in if you haven't seen it before. So just look it over. I hope that the ideas of the proof are getting across, because they're really they're not that difficult. It's just that I'm trying to get a lot of steps done very quickly. What I really want to get to is, what do you use this for? Oh, yes.
So at a high level, this sort of reminds me of the central limit theorem, where you're trying to find the difference between sort of an empirical mean and the actual mean. But we can't use that here because the function is random. Is that right?
Well, actually, so that's a good question. What is the difference between concentration of measure and the central limit theorem? So concentration of measure, that's a very good question. They're quite different, actually. So concentration of measure says the probability that x bar minus mu is bigger than t is less than something small. However, the central limit theorem is saying x bar and mu is converging to some like normal distribution. This is what you need to use to do inference. If you want to get confidence intervals, you need very precise statements. And that's where we use central limit theorem. This is more of a proof technique. This is more like we're going to say, I want to prove that empirical risk minimization is consistent, which is what we're going to do. It just says I need to get a probability. The probability bound itself is actually not very useful. In fact, it's usually got huge constants in it that are kind of useless. What's useful about it is the form. It's something going to 0 at some rate. So it helps us get rates of convergence, but it doesn't give you confidence intervals. This gives you consistency and rates of convergence. For inferential purposes, like confidence intervals, you need things like the central limit theorem and so on, which are a little bit more precise in some sense. Yeah. So what we're going to see, so I guess we'll do this before I start the Minimax stuff next week, is I want to show you now applications of concentration measure, which is probably the most interesting part. And it'll be pretty quick because now that we have the tools, it's just a matter of stating the results again. But I want to show you that we can show that we can get bounds on how good empirical risk minimization is. We can get bounds on k-means clustering. We can get bounds on kernel density estimation. So all kinds of bounds, rates of convergence, things like that come out automatically from concentration of measure. That's the usefulness of it. And so what we'll do is, I guess the plan next week then is we'll finish the concentration of measure by looking at some of the applications of concentration of measure. Then we'll switch to the next topic, another theoretical topic. I hope you're up for more theory. This is Minimax theory. And it's pretty cool stuff, I think. If you talk to some of the senior ML students, most of them are mired in Minimax calculations as we speak. And then at that point, what's the plan after Minimax? We haven't decided yet, right? That's when we're going to start doing extra topics.
Multiple options.
Yeah, so we still haven't decided what that'll be yet. Any questions? Yeah.
So all of these are about a binary function.
So that's a good point. So far, I've restricted myself to binary functions. Another thing I'll mention briefly next week, I don't think I'll go into the details, are things like covering numbers and bracketing numbers that deal with very general classes of functions. Yeah.
Like continuous functions? For example, continuous functions.
Yeah, or more general than that, yeah. Any other questions? All right. So see you next week. Take some time to look this stuff over on the weekend.